Hello everyone! Today I will be sharing the hardware design notes and application tips for the MA35 series. Firstly, regarding the power supply. The internal power supplies of the MA35D series chips are independent units. Therefore, whether or not certain functions of the chip are used, such as RTC, ADC, etc., all related power pins of the chip, such as VBAT, AVDD, must be connected to the corresponding voltage levels and must not be left floating. Some module I/O levels of the chip support 1.8 volts or 3.3 volts. When designing the schematic, match the I/O levels according to the peripheral devices connected. The table shows the power consumption data of each power supply measured when the MA35D16A887C is running data flow, driving the HMI display, and playing back H.264 video. By looking at these numbers, we can better understand the power consumption of each rail, which helps in selecting the right power supply ICS, designing the schematic and PCB correctly, and leaving enough margin in case the application's power quality is not ideal. When selecting a power supply solution, two options are available: a PMIC or a discrete DC-DC design. For a PMIC, the model must be chosen from the MA35D1 approved vendor list, and the schematic should follow the SOM development board as a reference. The communication interface between the MA35 and the PMIC is predefined in the default BSP using PD6, PD7, and PA15. This allocation should remain unchanged to avoid conflicts. For further clarification, the responsible engineering team can be consulted. For a discrete DC-DC solution, the power rails must be matched to the consumption of each supply, and the DC-DC and LDO components selected accordingly. In addition, the MA35 power-up sequence requires strict adherence. The IoT development board schematic should be referenced during circuit design to ensure compliance. In schematic design and PCB layout, there are certain specifications that should be adhered to as much as possible to avoid instability in the board operation due to arbitrary design practices. Therefore, we should ensure that for each set of VDD and GND corresponding to a chip in the schematic design, at least one 104P capacitor is placed. The recommended capacitor materials are X5R or preferably X7R. During layout, each capacitor should be placed as close as possible to its corresponding chip power pin. The trace width for power nets should be at least 0.5 millimeters or wider on the top and bottom layers. The farther the chip is from the power source, the wider the trace width should be appropriately increased. For 4 or 6 layer board, the trace width for power routing on the inner layers should be twice or more than that on the top and bottom layers. Whenever possible, use large area copper pores instead of traces for power distribution. For the main power traces that change layers, it is advisable to use multiple vias or increase the via diameter to meet the required current carrying capacity, ensuring a robust power supply. All chips in the MA35D series are equipped with an internal RTC unit. Specific functions can be found in the datasheet, and it can be used as needed. When the internal RTC is used, the schematic should follow the RTC section of the development board. On the reference design, the RTC-NRW, AKE, and RTC-RPWR pins are typically connected to a momentary switch and a 10 kΩ resistor to ground, pressing the momentary switch power on the board by waking up the RTC. At this time, the RTC-RPWR pin drives high to control the DC-DC-EN pin to power up the system. If a momentary switch is not required for power on, the switch on the RTC-NRW-AKE pin can be omitted. However, a 10 kΩ pull-down resistor must still be placed on the NRW-AKE pin to allow the RTC to wake properly. When the internal RTC is not used, simply provide a 3.3 volt level to the VBAT pin, place a 10 kilo pull-down resistor on the RTC NR.wake pin, and leave the other RTC-related pins floating. The MA35D series chips have two important external clock sources: the main clock at 24 MHz and the RTC clock at 32.768 kHz. A stable external clock source is essential for the reliable operation. Therefore, the schematic and PCB layout must be designed strictly according to the chip specifications. When designing the schematic, pay attention to clock frequency, RF parameters, and CL parameters, etc. During layout, it is important to achieve rational placement, proximity to the chip pins, short traces, avoiding layer changes, and minimizing interference from other components. In the USB section, one critical detail is the USB 0 ID pin. At power on, the external voltage level on this pin determines the operating mode. When the pin is high level, USB 0 enters device mode. When the pin is low, it switches to host mode. In the schematic design, the USB 0 ID pin is typically pulled up with a 10 kilo resistor by default. This sets USB 0 to device mode, which is commonly used for programming and debugging. If USB 0 needs to be switched to host mode, it is recommended to reserve a 0 ohm resistor to ground. The USB 0 volt bus VLD pin is used to detect whether USB 0 is connected to a computer USB host when it is in device mode. The typical practice in schematic design is to connect the 5 volt signal from the USB port to the USB 0 volts bus VLD pin through a voltage divider consisting of a 20,000 ohm resistor and a 39,000 ohm resistor. When not connected to a computer host port, this point is at 0 volts. When connected to a computer host port, the 5 volts from the computer USB host port is divided down to 3.3 volts through the resistors, which is used for detection by the USB 0 volt BUSVLD pin. The host bus power overcurrent detector pin HSUSBHOVC is matched with corresponding management circuitry in the development board schematic. By default, this pin is configured as a high level, and the accompanying code will monitor this pin. If a low level is detected on this pin, it will be judged as an abnormality, resulting in the USB host being unable to function properly. When designing the schematic, note that if the management logic part of the circuitry is omitted and not designed according to the development board schematic, the pin can be matched for use in two ways: hardware and software. The hardware approach involves pulling up the HSUSBHOVC pin to 3.3 volts with a 10 kilo resistor to keep it at a high level. When the HSUSHOVC pin is used for other functions and cannot be provided with a fixed voltage from the periphery, the issue can be resolved by modifying the software. For specific methods, refer to the relevant documentation or contact the FAE for assistance. The MA35 series chips support multiple boot methods. During startup, the boot method is selected by determining the voltage levels of the PG2 and PG3 pins. Each of the PG0 to PG7 pins corresponds to different functional configuration combinations, including boot methods and parameter matching for the selected flash devices. For specific details, refer to the chip manual. When designing the schematic, the corresponding voltage levels should be provided according to the project requirements. These pins can be multiplexed for peripheral applications, but the power-on voltage levels must be properly matched to avoid incorrect voltage detection during power-up, which could lead to boot failure. The PG0 to PG7 pins have weak internal pull-downs by default. A simple practice in schematic design is to reserve a 10 kilo ohm resistor for external pull-up. UART0 is a very important debugging interface for the A35 part in the MA35D series. Pay attention to bringing out the corresponding pins and reserving them for debug use. This is especially true for the BGA package. If the UART0TX and RX pins are not reserved and brought out, the PCBA will be impossible to debug once it is manufactured, and the only option will be to modify and remake the PCBA. The MA35D eMMC interface offers eMMC 0 and eMMC 1. eMMC 1 supports the highest HS200 rate mode. When using eMMC boot, it is recommended to prioritize the eMMC 1 interface, and the schematic design and PCB layout should be designed according to the HS200 mode specifications. Additionally, the MA35D BGA package supports both 4-line and 8-line modes, while the LQFP 216 package only supports the 4-line mode. The EPAD pin on the bottom of the MA35D LQFP 216 package chip, which has electrical properties, GND, serves as the main return path for high current during chip operation and also provides thermal conduction and heat dissipation functions. The quality of the soldering of this pin on the PCB directly affects the stability of the chip's operation. Therefore, in schematic design, PCB package design, PCB layout processing, and the SMT process, it is essential to fully understand this pin and design according to relevant specifications. PinConfigure is a software tool that assists in quickly configuring the functional pins of a microcontroller. Through this software, you can allocate the interface functional pins corresponding to the chip resources according to the project requirements. It is intuitive, fast, and error-free. Additionally, it allows you to save or import configurations for further editing and can generate initial pin configuration programs. The above introduces some precautions and application tips in the hardware design of the MA35 series, helping everyone pay attention to the key points of the design. Referring to the development board schematic and PCB layout before hardware design, and carefully reading the hardware development guide can reduce errors and speed up the project development progress. Goodbye.